We've got another exciting session lined up today, anisotropic thermal conductivity and composites. This lecture delves into the world of anisotropic composites and the groundbreaking measurement techniques applied to examine those materials. It's a review of the Anisotropic Thermal Conductivity and Composites presentation from the Advanced Materials Show US earlier on this year. So we'll be discussing how to utilize bulk and isolated TPS modules in conjunction with the absolute MTPS sensor to measure thermal properties in complex anisotropic composites. This information serves as a pivotal reference for those looking to understand and explore the thermal behaviors of such materials. Our speaker for today is none other than Dale Hume, the president of Thermtest. With over 20 years dedicated to the thermophysical instrumentation industry and a wide range of expertise, Dale is here to share insights that promise to be enlightening and transformative. So, whether you're a seasoned professional or just starting to explore the world of thermal conductivity, sit back, relax, and get ready to dive into a world where knowledge is always heating up. As always, drop your comments into the chat box below and Dale will answer them at the end during the Q&A portion. So without further ado, I'd like to pass the virtual stage to our esteemed speaker. Dale, over to you.
Thanks, Angela. Let's see. So can you see my screen, Angela?
I can't see your screen at the moment, Dale.
Okay. Share.
Oh, there it is. Now okay. I see it. You're good to go.
So today, thanks, Angela. Thanks for the introduction. And today we're going to talk a little bit about the anisotropic measurements of, the thermal conductivity of and anisotropy in polymers or composites. So the types of methods that Thermtest is involved with, bridge, transient, and steady state. They are, from this little graph, is sort of snapshot of the thermal conductivity ranges and methods, as well as temperature, transient plane source, heat flow meter, guarded heat flow meter, transient hot wire, transient line source. And they all have a special range of use. Some of them more flexible, some of them more focused. And that's really what the focus is today, is use of transient, the responsible use of transient methods, understanding the assumptions, some of the assumptions related to what the topic we're talking about, and how to sort of get the most out of those methods and know when to use steady state methods. So what is anisotropy? Anisotropy is basically due to a process or a filler introduced with a design element or purpose to create thermal conductivity or other related properties or other independent properties that differ in more than one direction. Typically in our industry, they are in plane and out of plane. Those tend to be the differences that we're looking to measure. And those tend to happen also with layered structures, whether they're repeating or non-repeating through the thickness. So a layered structure of a polymer and a metal, or a polymer metal, those all create independent directional properties when it comes to thermal conductivity. And an example of those might be pouch batteries or cylinder batteries. Those are anisotropic, as well as composites with a filler or layered structures. So measurement of thermal-physical properties, they typically fall into two categories, transient and steady state. These are some of the simple characteristics of each. Transient being short test times. Often the sensor is both the heat source and the temperature sensor. Across transient hot wire, transient plane source, modified transient plane source, they all use that same principle where a small amount of heat is introduced to an electrically conductive metal, whether it be nickel or platinum. And we look at as the heat diffuses away from that sensor, we're recording the transient versus time. We'll talk a little bit about that, the transient rise versus time. It does have the advantage of being short test times, but also the ability to measure or calculate thermal conductivity and often thermal diffusivity from the one measurement. So it's certainly attractive that way. Steady state typically has long test times into the tens of minutes. The configuration of the sample to the plates is there's a hot side and a cold side. Your sample's introduced. And due to the delta, there's a gradient across the sample, and that gives us thermal measurement. Once steady state conditions are reached, we get a measurement of thermal resistance, and with known thickness, a calculated thermal conductivity. And that has advantages for complex materials in layered structures that are not repeating. That's what we're here to talk a little bit about. So the related standards to each of these categories: transient plane source is an ISO method currently. There are drafts for ASTM within the E37 committee. That subcommittee is E3705. If anyone's interested, chat with us or go or search E37.05 on the ASTM website. You can see the information. You can join and be active if you're interested. The new standard is related to transient plane source, but unique measurements, ISO 22007-7. And of course, another classic method is the laser flash. Again, that's within E37, and that's ASTM E1461. That measures diffusivity. With known specific heat, you can calculate thermal conductivity. Steady state, a heat flow meter, which is aimed at insulation type materials, larger scale, where the sample acts as the guard itself, the passive guard. That's ASTM C518, and international standards of ISO also exist. The guarded heat flow meter, which follows the same delta T across the sample, but a guard is used as we minimize the radial sample size, that direction. A guard is used set to the mean temperature between the two plates to limit the delta radially, so that we get a high confidence one-dimensional gradient across the sample. And that lets us measure a much more wide conductivity range with the steady state device. So that one is aimed at polymers up to metals, where the heat flow meter is aimed at mostly insulators. So both of those are really good for complex materials, heterogeneous materials, and or layers that are non-repeating in their thickness. So what is modification? So we're going to talk a little bit about modification of the transient plane source. What is defined by modification? Modification is any change or any difference that is proposed to improve or alter a method. And the method we're describing is the transient plane source that was originally described in the ISO 22007-2. So the two versions of the modification of that are absolute. So what did we do? What was done to create an absolute version of the modification of that original method? And then the comparative MTPS or modification of that. What was done to create that? What were the advantages? So the absolute version, I have a sensor here. And this is basically, it's a very simple approach. And I'll show you the breakaway of this. You have a sensor sitting on top of an insulation, and it's permanently housed as an asymmetric sensor. But it follows all the exact same principles. The transient plane source method described in the ISO is absolute in nature. What that means: from the output of the instrument, the thermal physical properties are calculated. So nothing has changed from the theory point of view. It's just permanently housed in that single side or asymmetric configuration. So it has all the advantages of transient plane source method. Variable test times, that's key for testing into materials. No contact agent. Reason why is because we're able to identify and remove that portion of the time that's the contact resistance. So you don't need a drop of water or paste. It measures thermal conductivity directly, thermal diffusivity directly, and calculates volumetric specific heat. And according to the new ISO 22007-7, it also measures thermal diffusivity. So in addition to that, the ISO 22007-2, and I'll just refer to it as the ISO, it is able to measure other configurations and directions. So three-dimensional is bulk. That's what's described in the ISO for the absolute method. So this MTPS sensor is able to measure bulk properties, or an average, as well as anisotropy. So two directions, axial and radial, for thermal conductivity, thermal diffusivity. Slab, which is conductive sheets. So that'd be a thin material that you isolate through the thickness and look at the heat propagation in plane. So you can measure all of those asymmetrically, all because we've got the technology and the ability to configure that sensor permanently. And we have the sort of the math to support the use of that across all the variations of the traditional modules. So the breakaway of that, just show you what's underneath that, is, so this is a sensor just without the Kapton on top. So this is a Kapton polyamide sensor with a double spiral sensor in the middle. It's a little hard to see, sorry about that, but that sits dead center on top of this permanently configured, and this extra Kapton is stretched around that insulation. So essentially, the sandwich is insulation, which has a known property. We have a couple of variations of this depending on temperature range, sensor, and sample. So that configuration is, it's easy to calculate the losses, the heat that's going into this known material, so that you can calculate asymmetrically. So that's the configuration. That's all there is to this. If we take the rest of it apart, it would be electrical connections, and you can see through the plexiglass bottom that it's just the other side of this insulation. So there's nothing else to it other than a good design, smart design that lets us configure that in such a small format and it be robust. And that's what we get when we stretch this Kapton across that. And those are your 4 contact points that we'll speak a little bit about in a second on general theory. So the other version of the MTPS being a comparative approach, it is asymmetric, so single-sided. The reason why it is calibrated is due to the configuration, the construction of that. We'll show you a little bit about that. It does have fixed test times. The test times are fixed because that's part of the calibration. When you use, when the factory or if the user are able to calibrate that sensor, they need to isolate the range by having multiple calibration points so that that sensor can calculate the heat losses or calibrate the heat losses that are in the sensor. So it's not an insulation use, it's a different construction that allows that you have to associate multiple calibration points to populate the difference, the change, how much heat is going through the heat sink, through the sensor itself, and how much heat is going into the sample. There is a contact agent required because the portion of time that exists between the sensor and the sample is not known. It's not an absolute method, so that has to be calibrated. So you introduce a drop of water or a paste, whatever you're using, that is used between each calibration material in a calibration graph of thermal conductivity or thermal effusivity with 1 over slope, or the slope of that transient response gives you your known measurement. Here's an MTPS sensor, a comparative one. So you have a single spiral. It's guarded. That is sputtered onto a ceramic base. And then you have copper leads that bring it into a circuit board. And then it's just housed within a stainless steel. So there's no backing material that isolates the heat so that an absolute method can be calculated. Presently, that is done through calibration. So because with every unknown material, which anything from an insulator to a polymer to a conductor like a metal, the amount of heat that diffuses into the back of the sensor, all these conductors, is not known. It can't be calculated absolutely, unlike the transient plane source that's described in the ISO. So the only way to compensate for that, or to make that portion known, is to populate with a large number of materials over your range of conductivity or effusivity of your measurement. So that's a little description of the two, and to show the differences and what the strengths and weaknesses are. The strengths of the comparative are that you push one button and you don't have to develop parameters because they are calibrated into a range. And that does have value in some situations and applications. It's important to know the differences, but you do sacrifice some capability when you do that. So a little bit of theory on the transient plane source as described in the ISO. You have a double spiral that's insulated with Kapton or polyamide. They change in diameter based off of the sample size. So everything from 1 millimeter up to 60 millimeters in diameter. Of course, the more heterogeneous material is, the larger the sensor. That has many advantages. And of course, if your sample is physically small, you want to use a small sensor so that you're covering the diameter of that sensor by about 3 times the diameter of the sensor, roughly. When a measurement is made, a current is supplied to 2 electrical contacts. In the PowerPoint, you can see that as well as the video. These are 2 contacts. And then simultaneously, we're sensing electrical resistance. So, and that portion of time is into the second. So maybe 1 second up to typically 100 or 160 seconds. You can go much longer, but those are the typical ranges. We record a transient rise, temperature rise versus time. So that sensor generates a heat and as well acts as a temperature sensor to record the heat being pulled away or diffusing into the sample. And that we want to remove, so as it's an absolute method, we want to remove the portion of time that represents contact resistance. We want to make sure the heat we introduce to the sample never leaves the boundaries of the sample. So we have known dimensions. So with both the MP1 and the MPV, you input the dimensions of the sample, and our ITPS, which is our technology for intelligent transient plane source, automatically does a measurement to probe and reach the outer boundaries so that it selects a time sooner than that. So it generates power and time automatically as part of that intelligent algorithm. So measuring anisotropy with the transient plane source as is described and some other particular unique capabilities, the sensor is typically sandwiched two-sided. So there's a material, sensor, material. And if you have anisotropy, the assumptions for the anisotropic measurement are that the anisotropy is well organized. So that is a condition either of a filler that's well dispersed and aligning in one direction versus the other, or if it's a layered structure that they are repeating. That's really key. If it's not well defined, the assumptions, then the more it is not well defined or the more disorganized, the more potential there's for error. You'll get two directions, but that will influence the accuracy of each direction. So it is one of the approaches to that are to look at varying test times as you probe deeper into the sample. And if different test times give you different values, that's certainly a measure of the organization of anisotropy or the disorganization of anisotropy. Those are key tools that you can investigate. And of course, some of those, the typical approach is to measure as much of that sample as possible into the thickness so that if you do have disorganization, your value of axial and radial are accurate. That's a good strategy, but it does have limitations because if you're not measuring the full thickness and the penetration you have to use in the software comes from the thermal diffusivity, which is calculated, you can have error there. So it is something to be very aware of. The other capability are one-dimensional, where you look at a sample diameter that matches the diameter of the sensor. That gives you isolated directions. So that allows you to, for a complex material, if your materials are not well organized, you can isolate the radial direction and look at a taller sample, matching the diameter of the diameter of the sensor. So that gives you a better isolation of one direction. So the assumptions are not as wide. The other way is to look at slab materials, which isolate the thickness and look at the heat propagation in plane. So that allows you to isolate one of the directions and look at heat, the average of, if there is anisotropy in plane, then of course you're going to measure an average of that. So those are tools to isolate each direction radially, looking at heat propagation along the length of a sample, and thickness, looking at heat propagation along the in-plane direction. We use both of those in different ways, depending on how accurate the anisotropic measurement is. So there's a set of tools that allows you to investigate both situations. So again, a little slide showing the description of the absolute version of the MTPS sensor. It does follow the ideal theory of the transient plane source described in the original ISO. Is a permanent construction of sensor and insulation, ruggedly constructed to allow ideal measurements in a single-sided fashion. And that has advantages if your sample is large and hard to maneuver. If your sample is, you can place the sensor upside down and right side up. Or if you have a limited quantity of sample, you can test in a single-sided fashion with all the advantages of the original transient plane source, meaning the ability to measure all these different properties and directions with this sensor, as well as the intelligence so that you don't have to develop your own parameters. All you have to do is input the dimensions and the name of your sample, and it will pick the test time appropriate to dimensions to ensure you're using that the transient plane source method in its most ideal situation, which is parameters that allow you to test as much of the material as possible or directional. So with the absolute version of the MTPS sensor, this is a review, more visual, of what is possible with that sensor. So if you look at each one of these, the bulk, the sensor sitting between known insulation. So in this case, it's a known insulation on the backside of that test, which I showed you here. And then the sensor sitting on top. And again, this would be permanently stretched over the sample like this one. That allows you to measure three-dimensional thermal conductivity, thermal diffusivity, and a calculated volumetric specific heat and a calculated thermal effusivity. The second example would be anisotropic, which would allow you to, with one sample, measure in plane and out of plane for thermal diffusivity and thermal conductivity. So you get two directions, radial and axial. The third is slab, again, isolating direction and looking at heat propagation along the in-plane direction of a material. They tend to be sheets of metal, but you can also use it for lower conductivity materials, all the way up to several hundred watts per meter Kelvin. So it lets you isolate the direction. And the fourth one is isolating the in-plane direction and looking at a rod-like shape of material that matches the diameter or is close to the diameter of the sensor. And there's different diameters of sensors that allow you to accommodate different diameters of rod-like materials. So this is a visualization of what is possible with when you have an absolute version of that sensor. You have so much flexibility and taking advantage of ideal theory and higher accuracy because you don't have as much calibration effect when you use the comparative one. So we made some quick measurements to demonstrate the accuracy of the sensor. We took Torlon, which is a polyamide material used in friction applications. It is extruded, so that creates anisotropy because of the direction of extrusion. So you have a higher conductivity in plane than through thickness. We compared it with the manufacturer's results, which is Solvay. So we did measure, one of the inputs for anisotropy is volumetric specific heat. Unlike bulk, it has the output of conductivity, diffusivity, and specific heat. When you're measuring anisotropy, you need the input of volumetric specific heat. We measured that with the specific heat module on the TPS. So that's a direct measurement. Input that in, and we get, you can see from our results, we get in-plane values of 1.4 watts per meter Kelvin and diffusivity as well, and then through thickness or axial. And that axial value or through plane compares well with the spec value or the manufacturer's value, because that ASTM C177 is a steady state measurement where we're measuring through the thickness only. So that's good correlation. And that identifies certainly the performance of the sensor, but more importantly, what we're trying to show with this is when your material is well organized, you can get very good data using the anisotropic module using the absolute version of the MTPS sensor. So you can see this is a comparison. We did an additional test of guard heat flow meter where that sample is introduced between two plates. A guard oven is brought down, and you see there's pretty good correlation. This is another example using injection molded polymer. So the injection molded polymer creates anisotropy due to the direction of the injection molding. We measured the specific heat directly with the specific heat module, and you can see that the correlation is good, but not as good because you have this disorganization of fillers. And when we look at the anisotropic module and compare that to the GHFM through the thickness or axial, and that's what that is, it's not as good. Yet when we compare that to the one-dimensional measurement on the TPS sensor, it's better because we're isolating the disorganization in plane and looking at through thickness. So with the GHFM, that's ASTM E1530, and the one-dimensional measurement, we're isolating directions and looking at only one direction. So that gives us better correlation. Where looking at the anisotropic test, that has the assumption that it is well organized. And again, the higher degree of disorganization does create error. The more disorganization, the more error. This is one small example of a small amount of disorganization and the accuracy difference. That's still pretty good correlation, but it's a good example. We wanted to share a relatable example, and I think that's what this does. The radial direction, we only have so many ways of comparing this. We don't really have another technique that isolates the thickness value and looks at the propagation in plane. So what we're able to do is use the anisotropic test, the radial thermal conductivity from the anisotropic test, and compare it to the isolated slab. And again, you can see it supports that same measurement conclusion or theory that basically that disorganization does create a little bit of an error in the anisotropic test. Again, there's a little bit more confidence in the slab because we're isolating the thickness and looking at one direction, like 1D. So the key is really that if your material has disorganization and you have doubts about your axial and radial or out of plane and in plane thermal conductivity diffusivity, that you can isolate those two directions and measure it with the TPS method still. Or if it's highly disorganized, you can even use a steady state with a higher degree of confidence. So conclusion, the anisotropic module can be used to measure directional properties on organized anisotropic materials for both radial and axial directions. We have a lot of examples of this. We spent a lot of effort trying to look at the assumptions of this approach and suggest and describe how that can affect your measurements if you're a user. I think that's really important to understand the assumptions and the potentials for error, and then when and if a steady state method is needed. And why can we speak to that is because we make all of those methods. If one company only makes a transient method, they might not describe the use of steady state methods like we do, because we do manufacture them. We can speak to point. We know them both really, really well. And we know the impact of making bad measurements on the use in simulations, on the use of specification sheets, on the use of time and evolution of engineering principles. For samples that are disorganized and their anisotropy, again, that's fillers that are not well aligned or layers that are not repeating through the thickness. The slab module and the 1D module are better than just looking at the three-dimensional anisotropic, which has those assumptions. They are better. They do have limitations, but they're certainly better. And it's another tool to investigate your materials with that same transient plane source method to ensure you're getting good, accurate results. And a plug for ITCC, which we're hosting around this time a year from now in Virginia. It's the International Thermal Conductivity Conference. For those that are interested in the best measurements of thermal conductivity, and thermal conductivity has an impact on your business or your project, the people that make good measurements end up here, both from a user and development of methods. This particular show and conference rather has a long history of trying to make good measurements and inform the public and its members on good measurements. So I think that's all there is. And if there's any questions, as always, please reach out to us, and we're happy to talk more about this important topic.
Well, ladies and gentlemen, this was an exciting and enriching session. I hope you found today's webinar on anisotropic thermal conductivity in composites as enlightening as I have. Dale, I told you I would get the anisotropic eventually. I'd like to extend my heartfelt thanks to Dale for giving this presentation today and sharing your wealth of knowledge and wisdom with us. And as we conclude today's webinar, please remember, as always, you can send us an email with your questions if you have any. And if you join our mailing list, you can keep up to date on any webinars we have coming up. So if you would enjoy today's session, please complete the form on our website and subscribe to our newsletter. And once again, thanks for joining us today. And until next time, keep learning, keep exploring, and stay curious.
Thank you.